Hello, everyone. Welcome to today's live broadcast, Sartorius Inline Lysis System, the easiest alternative to batch alkaline lysis. I'm Shannon Stoltz, Senior Editor of Special Projects for BioPharm International, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by BioPharm International in Pharmaceutical Technology and sponsored by Sartorius. Sartorius BIA Separations develops best-in-class analytical and preparative chromatographic solutions for gene therapy and vaccines. The company's products, which are utilized in hundreds of clinical batches, are setting the standard for manufacturing highly complex large biomolecules, such as viruses and viral vectors, nucleic acids, LNPs, exosomes, and phages. Before getting started today, we do have a few quick announcements. First off, this webcast is designed to be interactive, so we encourage you to ask questions throughout the event. Any questions you have can be submitted by typing them into the Q&A box, which can be found at the bottom of the video player. You can enlarge the slide window by clicking on the small icon in the bottom right corner of the media player, and keep in mind that the slides will be advancing automatically during today's event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the top right of your presentation window. Moving on, I would now like to introduce our wonderful speaker for today. We are very pleased to be joined by Mateusz Krench. Mateusz has been with Sartorius BIA Separations since 2021 as Application Area Manager for pDNA and mRNA, and since 2023 has also operated as a Product Manager for the Inline Lysis machine. Thank you so much for joining us today, and please get us started.
Well, hello, everyone. Thank you for this very nice introduction. You already kind of described what our company is working on, and that's why I will not use too much time on the company, but I will tell you where I'm calling from. So for everyone who's not from Europe, I'm telling you that I'm calling from Slovenia, from a very small country from Central Europe. There's only 2 million of us. We're a chicken-shaped country, and our company is located in a town called Ajdovščina. If you have trouble finding us, you can find us on a chicken thigh. I would say that would be the most appropriate way. But otherwise, yeah, like it was already presented from the beginning, we are kind of a, we still call ourselves Sartorius BIA Separations because just recently we were bought or acquisition by Sartorius in 2020. But otherwise, BIA is a specialist in chromatographic columns. We are very good in monolithic stationary phase. So we use monoliths for prep and for analytics. And for everyone who doesn't know, monoliths are very good for handling very large molecules like pDNA and mRNA. That's why we're also very tied in upstream and downstream, not only in DNA or RNA, but also into bacteriophages and viral and non-viral delivery vectors. So when we actually are so involved in upstream and downstream, we saw that there is a gap and there is a need to also have something much better than a batch lysis. That's why I'm also presenting today an inline lysis. Yeah, also what you see here on the picture is kind of a new biotechnology campus that is being built here in Ajdovščina. Yeah, we're going to become like a hub for this part of the country. Okay, well, let's move on to the alkalizator, the inline lysis machine. We're just going to look a little bit of the importance on the applications of pDNA. We're going to look at the alkalizator at a glance, look at how robust it really is, look at the system as like a helicopter view. I'll show you some case studies, how it performs compared to batch lysis, and then we'll move to questions and answers. Yeah, well, importance and applications of pDNA. For everyone listening to this knows that pDNA is in high demand. You can find them. You can find pDNA in 3 main applications: directly as a therapeutic, indirectly as a raw material for AAVs, for example. Here it's especially challenging because you're using very large plasmids that are 18 kbs or 24 kbs or even larger than that. And also you can use pDNA indirectly as a template to produce mRNA. Yeah, mRNA. Just a few numbers that I just pulled in yesterday that last year, the pDNA market was estimated at 5.4 billion, which is enormous, and it's actually projected to have a compound annual growth rate of 20%. So this field is really kind of growing. So it makes sense to kind of invest in pDNA and look in the pDNA world, because yeah, a lot has been going on here. And yeah, this is the star of our show for today. This is our Sartorius inline lysis system. We call it alkalizator. The name kind of suggests that it's using some sort of alkaline solutions, and it does have like an aggressive name, you know, and we really like that name, you know. Usually people associate this name with something really strong, robust, like a Terminator or Godzilla. So yeah, so kind of stick with alkalizator. Otherwise, what you see here on the picture is the machine that has a tower and a lysis reactor. So the tower is multi-use, and the lysis reactor and all its tubes is meant to be single-use. This machine is fully automated inline lysis system, and the tube part and the lysis part is a closed single loop. Here in the lysis reactor, all the magic happens, you know, all the mixing in right ratios, all those residence times, all those neutralization, precipitation, flock forming that I will go into later on. All that magic happens here in the lysis reactor, and what comes out can then easily be filtered and also captured. So what you see on the picture is the machine that can process up to 10 kilograms of resuspended cells per workday. 10 kilograms meaning 10 kilograms of cell paste. Now, if you would dilute that with a resuspension factor of 10 times, meaning that you can process with this machine 100 liters of resuspended cells in 8 hours. That is the current kind of upper limit of the process with this lysis reactor, but we are already working with a larger lysis reactor that can handle 5 times more, meaning 500 liters of resuspended cells per 8 hours. So this machine is very compact. It can be at a tabletop, it can be on a trolley, and yeah, where could you actually put this machine in your process? Look, everyone is looking for a robust and consistent bacterial lysis. You know, if I talk with the people from upstream, they're always bragging about how high their specific plasmid yield is, and when you're talking with the people from the downstream, they're always bragging how high their capacity on the column is, and so on. But I don't find many people bragging about how efficient the lysis is. Yeah? You know, nobody really wants to work with lysis. It's a smelly business, you know, and kind of doesn't fit into place, you know. So we call this the lysis step as kind of a midstream process, you know. And usually what customers do, or what is kind of the golden standard, is a batch lysis, meaning you have a big vessel, you have a big propeller, you're pouring cells in, you're suspending them, you then add lysis buffer, you mix that efficiently as possible, and then you add neutralization buffer, you again mix that, and you add precipitation buffer, you mix that as much homogeneous as possible, and then just hope that this is a repeatable process. So I already kind of pointed out a few challenges when describing this process, and these challenges are large volumes. You know, for everyone who is familiar with batch lysis knows that scaling up is problematic. And when you are dealing with large volumes, then exposure time with your target pDNA and sodium hydroxide becomes problematic. And all that mixing also induces high shear forces, and these shear forces then will shear genomic DNA, making it soluble and problematic down the line, and also shearing your target pDNA. So what you want to do is to have a controllable exposure with sodium hydroxide and very low shear. So like you see on that picture on the right, you want your cells to be lysed on the cell wall and cell membrane just enough that the smaller molecules can become soluble and go out of the cell. But the larger molecules, especially genomic DNA, which is the most problematic impurity, becomes kind of a trapped or is not shredded to pieces. And alkalizator does this very well. Let's see how it does that. So here on the left side, we see the machine as it is. And on the right side, we see kind of a schematics that I will go through. So we have 4 peristaltic Watson-Marlow pumps. We also have 3 pressure sensors and 4 flow sensors, ultrasonic flow sensors. First, you start pumping cells and sodium hydroxide. So basically pump orange and blue. And this is then being pumped and mixed through the first mixer. This mixer is very, I would say, it has high shear because you have 2 solutions that are different in viscosities. So you need efficient mixing. So mixing cells and lysis buffer. These go together. And then when they're efficiently mixed, they continue through a tube part. So this is kind of I would say, a tube reactor, a long tube with a laminar flow, and the combined volume of this tube is 1 liter. I will explain a little bit later why this is important to have a defined volume. And then at the very end of this purple part, you have the green tube. So at the T part of the purple and green, this is where the neutralization happens. So you're also then pumping potassium acetate. And here, this is important, really important. You have lysate goo coming from one side and neutralization buffer coming from another side. And you have this very aggressive neutralization, which is then forming flocks and then pushed upwards where also air is added. Now, why air is important? Because you are reducing the viscosity, increasing the turbulent mixing, and also when the flocks are forming, they will capture some of that air and will float at the very end. Now, in this secondary mixer, this one is really innovative. The secondary mixer, highlighted in yellow, has efficient mixing, has really low shear, and is also also in this part we're adding precipitation buffer, which is calcium chloride. What comes out is a crude lysate, and this crude lysate, as you see, the flocks are on top. So we have this foam at the very top and this very clear solution at the bottom. For everyone familiar with the lysis, this is very good. This is very, because it means that the flocks will always remain on top and you can just start pumping from the bottom. So you're continuously pouring the crude lysate from the top, flocks will remain on top, and then you just continue to pump from the bottle and continue with filtration. And if you are using monoliths, you can also do inline dilution and capture. It's really important to do all these 3 steps in one day. I will show you some results later on that if you don't capture your target pDNA in one day, you will lose your target pDNA. Actually, you will lose your target supercoiled, because more supercoiled will just become more open circular. So more open circular over time, less supercoiled over time. So it's really important to process inline. Lysis, filtration, capture step. All right. So yeah, and this is how it's then continuously pumping. So it's just continuously pumping the solutions. The pressure sensors are monitoring that you don't reach over 1.5 bar. Usually working range is something in between 0.3 and 1 bar. So you are very below the 1.5 bar limit. The flow sensors are continuously measuring, and they're working in the loop with the peristaltic pumps. So if the flow is a little bit up, then the flow sensor will notice that and reduce the peristaltic pump a little bit, and so on. So it will continuously go for that target value. Yeah, so it's kind of a automatic mode as much as possible. Now, what this machine really needs, it doesn't really need much, basically. You just need one electrical plug, a basic electrical plug. Either in America you have 100 watts voltage, or in Europe 24, so you can have the whole range, no problem there. And you also need compressed air. This is a basic laboratory compressed air, so you just plug it from the back at starting back pressure of 7 bar, and the machine will automatically inside reduce those 7 bars to 2 bars, and what will come out in the lysis reactor is going to be something in between 1 to 2 liters per minute. So you're not adding that much. The combined weight of this machine and lysis reactor is approximately 55 kilograms. So it's not really heavy, it's not really small, it's a more pilot size, and the required space is approximately 80 centimeters times 80 centimeters. So you can easily put it onto a tabletop or on a trolley and use it when you need it, and then you can just store it away. So if this is maneuverable, then you can just have it on your trolley. When you need it, take it out, already have your buffers prepared, then just connect to those buffers, and then just start using it. Well, the tower, the GMP version of the tower is IP56, so it is dust protected, it is water resistant. It does have CUL for North America. It also has CE for Europe, and the software is also Part 11 compliant, basically meaning in the GMP world, you have all the audit trails, you have the traceability that is needed for a GMP environment, you have the alarms, the interlocks, yes, all the needed stuff for the GMP environment. The lysis reactor, as you see on the picture, this is slightly older picture, but the lysis reactor that you see here is 3D printed. It's 3D printed, but let me be absolutely clear, we are moving away from the 3D printed materials. These 3D printed components are not going to be used in the GMP environment because, yeah, we looked thoroughly into this and saw that, yes, over time, you will get particles out. Even though you are using biocompatible 3D printed material, for example, this is SLS technology, you can use PA 2200, a very standard material in the industry. It is USP class 6, but we don't want to use any of those 3D printed materials, so we're going to have molded plastics instead, covered with parlin. So all wetted parts are going to be USP class 6 without any 3D printed material. It will also be DSE, BSA, nitrosamine free, and will have all the needed certification for the GMP environment. In the GMP environment, you can use this lysis reactor once and then dispose it. But for the, let's say, the PD environment, you can reuse this reactor many times. Just have to tip it in between thoroughly with sodium hydroxide, circulate that, and wash it thoroughly with water, and you're ready to go to process another batch. Yeah, so this is basically the machine. Now, let me also show you some of the case studies. So the case studies that I will show you here, those samples were analyzed using our analytical column called CIMAC pDNA, and the chromatograms were analyzed on a PatFix platform, which is also our product. The CIMAC pDNA column also has a monolith, and that's why it's very good to quickly process large molecules like pDNA, and is also very robust, you know, so you can just use it over and over again, 50, 60, 80 times before you need to tip it. All right, so we have our first case study when we're comparing batch mode versus inline mode. So here we are looking at bacteria resuspended cells. These cells were DH5 alpha. We have a lot of experience with DH5 alpha, which is also kind of an industry standard. And the plasmid here, in this case, was approximately 7,000 base pair. And we are comparing batch lysis to inline lysis. And the volume of the batch lysis is very small, as you see here, only 20 milliliter. And if you're using small volumes in batch lysis, you have this efficient mixing. So it's very comparable to inline lysis, where you are in very small volumes. But once you scale up that to liters, 10 liters, to 100 liters, then this comparison starts to fade away. It cannot be comparable. Once you scale up, the inline lysis just becomes better. But nevertheless, let's look at the situation where we have the batch lysis in a small volume and inline lysis is 2 liters. The productivity is almost the same. Also, the quality is very much the same. Where it really differs, and this is something that I cannot stress enough, is the concentration of genomic DNA. With the batch lysis, you have 5 times more genomic DNA than with inline lysis. Now, we believe that the reason is because we just have the neutralization, which is much more efficient. Basically, what is happening when you are neutralizing? When you're neutralizing, the smaller molecules will kind of renaturate itself and become soluble, plasmids, small proteins, small RNAs. But larger molecules like genomic DNA, only if it will have enough time, will renaturate itself and become soluble. Now, if neutralization is really aggressive, then genomic DNA just doesn't have enough time to becomes soluble again. So we believe that the key here is in an efficient neutralization. That's why we are seeing less genomic DNA. The other thing is less shear. So if you are inducing more shear, then genomic DNA will just be shattered to smaller pieces, and those will then be seen down the downstream line, which you really don't want to see. So yeah, so this is kind of the first takeaway, that we are comparable with batch lysis. Inline lysis, batch lysis are comparable when you are working with small volumes on the batch lysis, and genomic DNA is 5 times smaller. Okay, another example showed here is, first of all, that we can also process complex samples like resuspended cells. We routinely analyze resuspended cells before we go into inline lysis. Why? Because we want to see how, or actually, we want to see in what shape are these resuspended cells. You know, if you have cells that are in real poor shape, they will already be kind of lysed from the start. And this is kind of a red flag from the start, because you will start with really high genomic DNA. This could be a problem or not, but just so that you are aware. And usually if cells are in really poor quality, you will see at the very bottom, you will see kind of a goo that is just mixing around and really does not want to resuspend. So if you see that, that is usually an indication that cells are in kind of in poor shape. So they are already kind of degrading, exposing their cytoplasm outside. So there's just something that you know. And how we do that, how we analyze that, we take a sample, a few milliliters, centrifuge that, take out the supernatant, dilute that by a certain factor, and load it directly to the TMAC pDNA column. Here we have an example of resuspended cells being analyzed, and you see that in between of open circular and super cold, there is a potato shape where you would find linear and genomic DNA. So the bigger that this potato shape is, more genomic or more linear pDNA there is from the start. So this paste, as you see here from this graph, this paste was not really bad, but it was not also really good, you know. But what I really want to show you here, that even if you don't have like optimal cell paste to be resuspended with or to start with, the alkalizator will still process that, and will still process that really nice. What we see after the process in the crude lysate, we see that the genomic part or the linear part is almost flattened. There's only like approximately 2% remaining, which is very good. So even if your cells are not like the best, if your upstream process is not optimized yet, and you're working with kind of a suboptimal conditions, you can still work with alkalizator and just process and get out as much as you need. Okay, another interesting observation that we usually look and usually see, and is that something that I already mentioned from the beginning, that you really need to process everything in one day. So lysis, filtration, and capture step all in one day, that is kind of imparable to do, because as you see here, we analyze the same sample, the same fine filtered lysate. So this lysate was not the one with the foam and all those impurities seen inside. This lysate was already filtered, so it was already cleared. So you would think that, well, if we have a cleared lysate, then our target pDNA is in no danger. But you would be wrong. Your target pDNA really doesn't want to be in those harsh environments. That's why it really needs to be pulled out as much as possible. That's why you need to go to that capture step at the very end as soon as possible. We see that after 1 hour, we have approximately 7% of open circular and 89% of supercoiled. After leaving that same fine filtered lysate at +4, so in a refrigerator, that concentration of open circular doubled. And if you leave it at room temperature, that concentration of open circular will triple. And will triple just on the fact that you have less supercoiled. So here we are seeing nothing else than just from one isoform to another. Now, if you still want to work with open circular, no problem there. But if your target is to get as much supercoiled at the end as possible, then it makes sense to process here as soon as possible. Okay, well, this is a 4th case study. So this is also kind of an interesting one for an interesting webinar like this one. So we also used alkalizator as a screening tool to optimize neutralization and precipitation step. As you remember, so first you're pumping cell and lysis buffer, then these cells are lysed, and then at the very end, they are neutralized and precipitated. So you can just play around with neutralization and precipitation. Now, here what we see is that we started with a dilution factor of 10 times. In all these 6 cases, 10 times dilution factor, meaning that if you start with 1 kilogram of cell base, you will end with 10 liters of resuspended cells. The lysis buffer ratio to cell, usually what we do is in 1-to-1 ratio. The lysis buffer basically contains sodium hydroxide and sodium sulfate. And the residence time, we usually go with 2.5 minutes. Basically, what this means is just in your target pDNA will be exposed to sodium hydroxide for 2.5 minutes. What we usually see is with inline lysis, you can actually reduce the residence time and still have the comparable results compared to batch lysis. We believe that is the case because the mixing is just so much more efficient. And then we have 3 parameters that we can actually play around with, which are potassium acetate for neutralization, calcium chloride for precipitation, and also the addition of air. I haven't talked much about air. I just mentioned it, that we're adding it to reduce the viscosity, increase the tolerability mixing, and also these flocks when they're forming. So flocks when they're forming neutralization, potassium acetate will react with sodium sulfate, will make flock. And if you're also adding air, that air will also be stuck with a little bit with those flocks. So that will also help them to float faster. So here we also played with air, 0.8 liters up to 0 liters, up to 5 liters at the very end. And here you can already visually see what are the differences. Some samples are more opaque, some samples are more clear, some flocks are bigger, some flocks are smaller. For example, if we just look at the flocks and the very extreme, we can look at the number 6 at the very bottom right corner. We see that the solution is clear, but the flocks are very, very, very small. So although this looks as a preferred way, you really don't want to have flocks too small. This is something that everyone kind of has experience from the lysis. If you have these really small flocks, especially this happens in the batch lysis, if you have really, really small flocks, they're like almost like sand-like, for some reason they just jam your filters. They would just jam your filters really fast. You know, the back pressure that you would see would just slowly kind of rise, and then just quickly just jam your depth filter and fine filter. So you really don't want to have your flocks super small, and you really don't want to have your flocks really, really large, you know. So kind of the ideal way is to have your flocks like a snowflake shape. So there is enough solution around the flock that pDNA can leach out. And yeah, if you have a very small specific plasmid yield, then it makes sense to have a higher dilution factor, so you will have more solution around the flocks, meaning you will leach out more pDNA. But the downside in that case is that you will also have larger volumes. Okay, so we produced 6 samples. These were actually produced in line, so you just go from one parameter to another, to the third, to the fourth, to the 5th, to the 6th. So you can have like 6 samples in 6 minutes. And you then take out samples, centrifuge those, dilute the sample, put it on the CMAC pDNA, and compare the results. And then you can see what are the true differences between each of the parameters. For example, with the sample number 6, this is where we were using the high flow rate of air. So here we were actually using 5 liters per minute, meaning air was really at the top. Mixing was really efficient. Flocks were really small, but our analytics showed that we also got out more linear and genomic DNA. So this is not good. You really don't want to damage your genomic DNA, your target pDNA. So already this was kind of above that threshold of what the pDNA still stands. Yeah, another, for example, where we got a lot of open circular at the parameter number 1 is seeing that we used less potassium acetate. And for some reason here in this combination, we got, let's say, 14% of open circular. So you can kind of quickly optimize your parameters and then just transfer those to the GMP production or production. Okay, well, another slide that I want to show you is how fast we were actually able to produce that. So this machine is actually, I would say it's from start to finish approximately 2 years. In January 2023, we already had our first beta unit. And here we have a picture with all 4 inventors. And the first beta unit was already then installed at our development partner in February. And in May, we also installed another 2 units in the United States. And then we got a lot of feedback from these customers. So we already kind of designed a new concept, how the machine should look like. So the new tower, new lysis reactor, and we went deep dive into the GMP documentation. We already had our first FAT in August, and in December, we already installed our first proper GMP unit at our developing partner in North America. So this was a really high pace, high intensity from beta to GMP, and we are really proud of it. So yeah, really happy to be part of that team. So all thanks to inventors and to our management to believe in us. Okay, so we're almost at the very end. So questions and answers. And now I'm actually happy to take your questions. I hope this presentation was interesting. I believe there might be a lot of questions, but otherwise, yeah, this was fun, and I'm looking to go into a little bit deeper discussion. Thank you.
Perfect. Thank you so much for that informative presentation. Before we get started on that Q&A session, I would like to quickly remind the audience how to submit questions. You can submit your questions by typing them in the Q&A box, which can be found directly below the video player. So our first question for you today is, the presented system uses 4 solutions. Could it also be used with just 3 solutions?
Yes, that's a very good question. So the system is designed to use, or primarily designed to use 4 solutions. So resuspended cells, lysis buffer, neutralization buffer, and precipitation buffer. But if you have a different combination, a different batch recipe, then you could also use just 3. Yeah, just let's say the last one would then be closed, and then you're just mixing with 3. So yeah, it is possible.
Wonderful, thank you. Moving on, what kind of filter are you using, and is the filtration also operated in a continuous way?
Yes. So the filters that we are usually using here at Sartorius is it's actually our Sartorius filters. So first one is the depth filter inlined with a fine filter. So the depth filter is a PP3, so polypropylene filter with a 20 or 50 micrometer filters, pore size. And the fine filter is Sartopore 2, a membrane filter with a pore size of 0.45. So yeah, these 2 filters are inline, and yes, they can be used as an inline also filtration step. So you saw that all our crude lysates had the foam on the top. So you're just pumping from the bottom directly through those 2 filters, increasing the filter life, and we calculated that you can increase the filter life by a factor of 10. So 10 times smaller filter for the same situation as you would do in a batch lysis. Okay.
Perfect, thank you so much. Moving on, what is the residence time distribution of the tube part?
Sorry, can you repeat that?
Yes, absolutely. Sorry about that.
Yeah.
What is the residence time distribution of the tube part?
Oh, yeah. Very good question. I probably wasn't spending too much long enough time to explain that. So the tube part has a dedicated volume. In our case that I presented, the dedicated volume was 1 liter. So if you're pumping cells and lysis buffer each 100 mils per minute, meaning 100 plus 100 equals 200. So 1000 divided 200 equals 5 minutes. So if you're pumping lysis buffer and cells at 100 milliliters per minute each, that corresponds to 5 minutes. So if you would pump 200 plus 200, making 400 in combined, then that would be a residence time of 2.5 minutes. So the flow rate then regulates the residence time. Okay.
Fantastic, thank you. The audience would also like to know, what was the model plasmid?
The model plasmid, so we are actually playing with different kind of plasmids. We really like to play with different kind of plasmids to really see what is the distribution that this machine can handle. And Our usual go-to plasmid is 4.7 kilobase. This one is a go-to, but we have a lot of experience with the plasmids that are used in the AAV production. So helper plasmids that are approximately 20,000 kilobase, rib cap plasmids that are even larger than that, around 24,000. And we see that this machine can process small plasmids, large plasmids, and really gigantic ones. I don't have much experience above 24,000. We haven't tried those, but yeah, if somebody wants to like collaborate with really large plasmids, then we can arrange on that as well.
Perfect. And then moving on, how soon will the GMP version be available?
So the GMP version was kind of a pre-launched just last week, basically. We had our Monolith Summer Symposium in Portoroz. This is a bi-yearly event of via separation, and we kind of showed to the world this machine. Before that, this machine was very much under the radar. Even now, if you would Google for alkalizator, you would probably not find you will probably not find much about it, but we are at the moment seeing that there is like a lot of need for this machine, and if somebody is interested, we can actually deliver this or resolve this case by case.
Wonderful, thank you. On to our next audience question. How is the mixing achieved in reactor 2?
Yes. Well, so yeah, the one who is asking that is probably asking about that secondary part where you have neutralization, precipitation, and mixing with air. So there we have a static mixer with a very innovative design inside. So a lot of R&D went into that, and it's also patent pending. What we really want to achieve at that very end part is to have something that efficiently mixes, but with really low shear. So basically, you are mixing solutions, but in combination of air, you are just kind of mixing efficiently with high turbulence, but very low shear, making this, yeah, great. Because for everyone who is familiar with the batch lysis, knows that once you add neutralization buffer in, you actually have to wait a few minutes, usually like 10 minutes or 15 minutes, because first you have neutralization, which is an exothermic reaction, and then you also add precipitation buffer and wait for those flocks to actually start separating. Here, because everything is done in very confined space with addition of air, you don't need to wait. You can use the buffers that are room temperature, and you don't need to be afraid for that exothermic reaction, because that excess heat will quickly be dispersed. Okay, a little bit more than answer the question, but I hope I answered your question.
It was wonderful. Thank you very much. And then what is the mixer mechanics or material?
Mixing material. What is this? Probably what is this lysis reactor made of, right? So I mentioned that on the pictures we are gonna. I showed you on the picture the lysis reactor that is 3D printed. We are moving from this technology completely, and in the future we will have the same architecture, same functionality, but it's going to be molded plastic or covered with parylene, so to achieve that USB class 6.
Perfect, thank you very much. And then is it possible to have closed loop control with the system?
Closed loop control. So probably referring how much solution you still have in your how much resuspended cells you still have. Yes, it is possible. Now I have to go 2 steps back. So imagine an operator who starts each day, prepares the buffers, prepares the machine, prepares the final container, and then it also puts in the parameters. So sets up the machine, sets up the lysis reactor, and adds in the parameters, how much volume of the lysis buffer you still have, how much, what is the volume of resuspended cells, volume of potassium acetate, volume of calcium chloride, and machine will regulate or will kind of count how much is left. And if it reaches 0, it will then ask you either, do you want to continue or do you want to stop? So if you want to refill, you can quickly refill and just continue the process. Yeah, you can just, you can work in this continuous mode.
Great, thank you very much. Moving on to our next audience question. Are the used mixers for the first and second mixing identical?
No, they're completely different. The first one is really high shear mixing, because first you need to mix two solutions that are really different in viscosities, and you need to have this very efficient mixing of cells and lysis buffer. So the first one is high shear, but the second one is really, really low shear. So they're kind of a completely different in geometry.
Perfect. Thank you very much. On to our next question. How long and how many times can one lysis reactor be used?
Yes, this is a very good question. So we are seeing this with the plastic reactors. We're seeing this with 3D printed ones that you can use them many, many, many times. Of course, this only applies for the research, for the process development environment. This should not be practiced in the GMP environment. I hope this is completely clear. In the GMP environment, it's only kind of a single use, but in the PD environment, you can reuse it many times. What we usually propose is just to sip it with sodium hydroxide, 0.5 molar or 1 molar sodium hydroxide for 15 minutes. Circulate that, just put the end tube back to the starting container, and then just circulate that for 15 minutes. So you will dissolve all the remaining impurities, cell debris, pDNA, and just then wash it with water, thoroughly wash it with water. Take a sample of the water, see the pH, and if the pH is close to 7, then just purge it, and you're ready to go to do process another batch.
Fantastic. Thank you very much. The next audience question is asking, could this system be coupled with other systems?
Yeah, this is a very good question. This system, yes, it can be coupled with filtration stage or filtration skid, but the communication between a skid, if it has a computer, and alkalizator, that communication needs to be done in a special way. There's no like a button that would sync with Sartorius filtration skid. So if you're asking how you could actually couple this, you would couple it directly with a filtration skid, having a depth filter and a fine filter and a peristaltic tube. So that's basically what you need. You need a peristaltic tube and 2 filters, and what you get out is a fine filtered lysate that can then be further pumped out, diluted, inline diluted with water, and loaded directly onto the DEAE column. So DEAE column is basically a monolith that we produce and can handle a large volumes. So no problem with volumes. You can just inline dilute and then just load it directly onto the column. And then when it's full, just wash it, elute it, and you have your pDNA stored. Okay.
Perfect. Thank you. Moving on to our next question, how do you treat the HPLC sample of resuspended cells before lysis? Would that just be centrifugation of the cells?
Yes, exactly. So you have your cells that are completely resuspended. So meaning you will already be kind of waiting for approximately 1 hour to really thoroughly resuspend all the cells. And just before you start the lysis, just before you start pumping the cells, you then take a sample, take few milliliters of resuspended cells, as much homogeneous as possible, and then you have to centrifuge that. We suggest you centrifuge that at high speed as much as possible, and then only take out a supernatant. You need a very small part of that supernatant. Dilute that to reduce the conductivity, and then you can load it onto the CMAC pDNA column, and you will see that plot that I showed you in the presentation in 17 minutes. So we can already kind of in 17 minutes see what is your starting position, focusing primarily on that potato shape where all the genomic and linear pDNA is holding. So if that potato shape is really big, like I said, that could be a potential red flag. If that potato shape of linear genomic DNA is very low, that means that your cells are in really good shape and you probably have your lysis more in control. All right.
Fantastic. Thank you very much. The next audience question wants to know, what is the quantification for gDNA?
Yes, for gDNA, we usually go with the qPCR. That's kind of the standard way to do it. This and CMAC pDNA. So, but if you really want to quantify it as much as possible, then we usually go with the qPCR. That's like the way to go. But if you want to quickly analyze it, to quickly see how much genomic DNA there is, you would again then treat that sample with CMAC pDNA column and just see what is in that middle part. So yeah, you have actually two options, either way. The third one would be, the third one would be my least preferred one, which is agarose gel, but yeah, not really a fan of agarose gels, it just take too long.
Perfect, thank you. And do you have any graphs of residence time distribution for the two-part of the alkalization?
Graphs of residence time. So I think if the person is asking about how the flow rates affect the residence time, so what we usually work within the ballpark for the residence time in our case is between 2 minutes and 5 minutes. We believe that is the working range that covers 99%. It really doesn't make sense to go to residence times of 6 minutes, 7 minutes, or even 10 minutes because you will start to degrade your target pDNA. The sodium hydroxide will just kind of start attacking your pDNA, and you will just see more open circular. So it really doesn't make sense to go into that really 6 minutes, 7 minutes, 8 minutes. And it also really doesn't make sense to really have like really short residence time, basically meaning 1 minute of residence time. In 1 minute, you can still process, but the recovery will be much smaller. In 1 minute, you will not efficiently tackle or destroy the cell wall and the cell membrane. Yeah.
Perfect, thank you. And do you add any filter additives like diatomaceous earth?
No. Diatomaceous earth is, we don't work with that. We have membrane filters and we have depth filters, and they work just great. Especially if you are using, especially if you are just pumping a cleared part of that crude lysate, if you just leave those flocks at the top, just pump from the bottom as much as possible. You can just use regular filters. We use just Sartorius filters. First one is a depth filter, PP3, 20 to 50 micron pores, and the second one is a fine filter, Sartopore 2, membrane filter, 0.45 micrometers in pore size.
Perfect, thank you. This next question is saying, I understand about the mean residence time, but what is the residence time distribution at high pH?
I don't understand the question. The residence time distribution at high pH. Yeah, high pH starts from the very early at the very beginning. When you start mixing cells and lysis buffer, then you already are in that above 12 or 13 pH. So that is actually the starting point, and the end point is when you neutralize. So when that lysate goo then meets the neutralization buffer and then is pushed upwards. So that is the residence time from the very beginning to the very end. I hope I answered the question. Otherwise, we can kind of have like a follow-up on that one.
Perfect, thank you. And what differences in isoform percentage have you observed when altering residence time or flow rate in mixer 1?
Again, can you repeat the question?
Yes, absolutely. What differences in isoform percentage have you observed when altering residence time and flow rate in mixer 1?
Oh, yeah. So if you go with with shorter flow rate, you will increase the residence time, especially in larger plasmids. I've seen that in larger plasmids. So if you have larger plasmids, talking about 20,000, 24,000, if you increase the residence time to close to 5 minutes, then it's more likely that they will get damaged. Basically, you will get out more open circular. So it really makes more sense to have a shorter residence time for larger plasmids, just so that they are not exposed to sodium hydroxide for too long. That's especially problematic with large plasmids. That's how I see it. What others here? Yeah, that would be the main one. The other important thing here to mention, I already mentioned this slightly during the presentation, is the dilution factor. Especially with large plasmids, it really is important. Or if large plasmids are really important for you, for example, you have a really poor upstream, you are only producing very low concentration of really large plasmids. If you want to kind of salvage on those large plasmids, then it makes a lot of sense to dilute those cells as much as possible, and your target pDNA will be exposed to solution more, and you will leach out more your target pDNA, more of this large pDNA. On the topic of dilution, this is also something that is always a fun part to discuss. Is usually when people ask me, well, I usually get when I'm analyzing concentration of pDNA with a kit, standard kit, the big firms, you take a sample and they say that dilute this sample by a factor of 50. This is a really high dilution. You take a sample, you dilute it really high, and then you perform the lysis, neutralization, you centrifuge, put it on a frit and elute, and then analyze that on a nanodrop, and you get a really high concentration on a nanodrop or a UV analysis. So this dilution at the very end is important, but usually in the process, it really kind of cannot go through. If you start working with large volumes at the very beginning, you will have 4 times larger volumes at the very end. So you really have to be kind of a pragmatic. What would be the starting dilution factor? But if you're upstream, usually how I say it, usually when they ask me what should be the dilution factor, then Mateusz, you know these things well. So usually I say, if your upstream is really good, then go with the dilution factor between, let's say, 8 times, 10 times, something like that. If your upstream is really poor, but you still want to salvage as much as possible, then go with the dilution factor of between 10 and 20. But above 20 times dilution factor, we really don't, you don't want to go above 20 because the volumes just get so enormous that it's really hard to process those very large ones. Although they are in line, so you never have a tank that is 20,000 liter, it's always continuously flowing. Still, the volumes are just large. Yeah. So, okay, this was kind of a really long answer. So I think can we kind of put a segue here? This was a last question.
Yes, absolutely. And we did get a lot of great questions today. So anything that we didn't get to, we can get to offline. So no worries about that. With that, it is already time to wrap up. So I would like to thank the audience for attending and participating in today's event. And I would also like to thank our sponsor, Sartorius BIA Separations, for making today's educational webcast possible. We would also like to ask everyone in the audience to participate in a brief survey. This survey will appear on your screen after today's presentation has ended. And you will also receive an email alerting you when this webcast will be available for replay. And we invite you to forward that announcement to your colleagues who may have missed today's live event. We hope to see everyone next time. Thank you and take care.
Thank you. Bye-bye.